So today we're going to go ahead and talk about 2D momentum conservation. So we know that momentum is a vector, so we have to realize momentum is conserved in the x and y direction separately. So let's go ahead and solve a problem together using this good old recipe. Okay, so first thing we do is we always sketch a before and after picture for our problem. So let's go ahead and do that, and I encourage you to do this yourself and then check back into the video. Okay, so I have two ice skaters, Daniel, who is Daniel, who is 65 kilograms, and Rebecca, who has a mass of, Rebecca is 45 kilograms. Cool. They're both, very happy. They are, ice skating along. Daniel stops to tie his shoelace. Okay, so he's stopping, so I know his velocity is going to be 0. And while at rest, is struck by Rebecca, who is moving at 13 meters per second to the right before she collides with him. So I will go ahead and draw her going to the right, 13 meters per second. Cool. After the collision, Rebecca has a velocity of magnitude. So this is the before. I should label that. And then after, So Rebecca has a velocity of magnitude 8 meters per second, an angle of 53.1 degrees above the horizontal. So Rebecca is going to go, up this way. Velocity is 8 meters per second, and this is 53.1 degrees. Okay, both skaters move on the frictionless horizontal surface of the rink. What are the magnitude and direction of Danielle's velocity after the collision? So I want you to think to yourself, what direction does it make sense for Danielle to go if momentum is conserved? Okay, so thinking about this conceptually, it makes sense that Danielle is going to go at a downwards angle because it looks like the total momentum in the y is 0 beforehand, so that has to be it afterwards. So Danielle has to go kind of at a downwards angle for momentum to be conserved. Okay, so we did our before and after picture, and this is our question mark, and same with this. Okay, now let's define our coordinate system. So I'm going to say y direction is up and down direction, where we say upwards is positive, and I'm going to say x direction, where to the right is positive. Cool. Now what let's do is let's go ahead and break vectors into components. So even before I break vectors into components, I should go ahead and find the momentum of each thing. So let's go ahead and start. So momentum of Rebecca initially is what? Mass, we know, times velocity. So this is going to be 45 times 13, which I get 585 kilogram meters per second. Momentum of Daniel beforehand is mass of Daniel times velocity of Daniel. Mass is 65, velocity is 0. Perfect. Daniel is just at rest. Momentum is 0. Okay. Let's look afterwards. Rebecca is mass times mass of Rebecca times velocity of Rebecca. So this is going to be Rebecca's mass is 45 times 8, which I get 360 kilogram meters per second. Cool. And we don't know Daniel's after momentum. Okay, so cool. And I should, what I should do just so I remember this. Rebecca's mass is 45 kilograms and Daniel's is 65 kilograms, just so I don't make silly mistakes. Cool. So, okay, now we need to break vectors into components. So Rebecca's, that's just initially x. Daniel just initially nothing. Rebecca is both afterwards. So I'm going to split that momentum into the x and y components. So let's go ahead and split this up. So this is 360. And let's see, this angle is 53.1 degrees. So momentum of y, let's see, so this is, we have opposite angle and hypotenuse. That's going to be sine of 53.1 degrees equals py over 360. So multiply both sides by 360, and I get py to be 288 kilogram meters per second. Okay, so px, that is going to be adjacent hypotenuse, so same idea, that's going to be 360 sine, or excuse me, not sine, cosine, silly mistake. Gosh, watch out for those darn silly mistakes. So cosine of 53.1 degrees, which I get 2 16 kilogram meters per second for this. Okay, cool. Okay, so to solve these problems, I like using a momentum table just because I think it helps me avoid silly mistakes. So what I'm going to go ahead and set up is I'm going to set up your R before situation and R after situation. So, and then we'll have both the X direction and we'll have both the Y direction. And keep in mind, momentum is what's conserved. So the units need to be our units of momentum, so mass times velocity, which is going to be kilograms meters per second. Cool. And beforehand, we have both Rebecca and Daniel separately. So I'm going to call it, we have Rebecca. Oh my goodness, I'm going to need to make myself a little more room. So we'll have Rebecca beforehand and Daniel beforehand. So we'll have both of those. And then afterwards, we will have, they're both separate. So we're going to have Rebecca separate and Daniel separate. Cool. So what I want you to do is go ahead and just take a guess for what you can fill in for the blank for each of these. So you'll learn more taking a guess yourself and then checking back into the video. Okay, so let's see. Rebecca is initially for the X direction, so right over here. She's just moving in the X direction and her momentum is 585 in the X. Her Y momentum initially is just 0. She's not moving in the Y. Daniel initially, he's not moving at all. So this is just 0 and 0. Okay, afterwards, Rebecca for the X, she is moving, this is her X afterwards, 216. Her Y momentum is positive 288. Cool. So what to think about is we need to figure out Daniel's momentum. So I think about like this big old blank we need to figure out. So we know momentum is conserved in both the X and Y separately. So initially, let's look at the Y. Initially, the Y is just 0 and 0, which is just going to be 0 total initial in the Y direction for momentum. Afterwards, Rebecca has 288. So if there's supposed to be 0 at the end, then this just needs to be negative 288. Cool. So that's going to be Daniel's momentum afterwards. And again, we knew that because the total Y momentum is 0. Okay, so now let's look at Rebecca. So initially in the X direction, initially there is between Rebecca and Daniel, there's 585 initially. Afterwards, Rebecca has 216 kilogram meters per second. So Daniel has to have whatever is left afterwards. So I think of that as, that's going to be what? 585 minus 216, which I get when I do that math, 369 kilogram meters per second. And again, I think of this as like a math statement. So it's like 585 plus 0 equals 216 plus whatever Daniel says, 369. Same thing over here for the Y. Cool. So it's like a good old math statement. Keep in mind, momentum is what is conserved, not velocity. People oftentimes make silly mistakes on that, but remember, momentum is conserved. Okay. So now that we have Daniel's both X and Y momentum afterwards, let's go ahead and draw that into our picture. So I'm going to go ahead and draw, so we know Daniel down here. So this is our friend Daniel. So his X momentum is whatever we got here on the table, 369 kilogram meters per second. His Y momentum is negative 288 kilogram meters per second. And we know it's a right angle between the X and the Y. Okay, so now what I want you to do is think about how do you find the total momentum. So total momentum, when you know the X and Y and it's a triangle, oh my goodness, good old Pythagorean theorem. I ignore the negative 288 and just call it positive, but again, you'll be squaring things with Pythagorean and negative squared is a positive, so it doesn't really matter. So total momentum of Dan is going to be what? A squared plus B squared equals C squared, so then you take the square root. So that's just going to be the square root of what? 288 squared plus 369 squared, which I get that momentum to be 468 kilogram meters per second. Okay, so now what I want you to remember, that is the momentum of Daniel. That's not the velocity, so we now need to figure out the velocity. So if I know the momentum of Daniel is 468 kilogram meters per second, I know momentum is what? Mass times velocity. So the mass of Daniel, so again, this is 468 mass of him is 65, velocity I want to find. And so I get the velocity when I do a little bit of math. I get 7.2 meters per second. Cool. And you know what? I should call that the speed because we don't, now I still need to find the direction. So the speed is 7.2 meters per second. We'll figure out the direction so we have the total velocity. Okay. So now let's see if we can figure out this angle. So what do I look at? Oh my goodness, we're just dealing with a good old triangle. So I'll go ahead and pick two sides. So I'm going to say I want to look at this side right here. That's the opposite. And I want to look at this x side right here. That's the adjacent. So let's go ahead and set this up. So if I have opposite and adjacent, that is going to be tangent. I want to find the angle, so it's going to be inverse tangent. So inverse tangent of what is it going to be? 288 over what? 369. And I get 37.9 degrees. Perfect. So what I would do if I was writing that in a problem, I would say the speed of Daniel is 7.2 meters per second at 37.9 degrees below the horizontal, or I would just draw a little picture and draw that angle in on the picture. Okay, and one last little thing, when you're finding an angle, you need it in degrees, so make sure your calculator is in degrees, not radians. Okay, so I'm going to show you another way to solve this problem and again get the same answer, which we said the angle was 37.9 degrees and the velocity of Daniel we said was, what was that? I forgot to write it down. That was 7.2 meters per second. So I'm going to just show you a different way that I like to do this using a little bit more algebraic. So what I'm going to look at is, okay, so we're going to set up essentially x momentum. So for the x momentum, we have the before and after. So let's look. So we have mass of Rebecca, velocity of Rebecca, plus what? Mass of Dan, velocity of Dan. And again, this is all the x. So I'm going to just put that on there. Equals what? Mass of Rebecca, velocity of Rebecca in the x, plus mass of Dan, velocity of Dan in the x. Okay, so now let's kind of think about what to plug in. So mass of Rebecca, what? 45. Her initial velocity is just the x of 13, plus mass of Dan is what? 65. His initial velocity is just 0, equals mass of Rebecca afterwards, 45. We need to find her velocity in the x. We're also going to do that in the y. Let's just go ahead and do that right now. So velocity y and velocity x. Okay, so let's do the x first. So if we're doing the x, we have adjacent and hypotenuse. So we're going to have to use cosine. So it's going to be what? Cosine of 53.1 degrees equals Vx over 8. So when I do that out, I get 8 cosine of 53.1 degrees, which is, what is that? 4.81. Oh my goodness, whoopsies, I'm not leaving enough space. Okay. There's a lot in this problem. So that is what? 4.8. I should say 80. So now I can put that over here. Velocity of Rebecca in the x is 4.80 plus mass of Dan is what? 65 times velocity of Dan in the x. So his velocity is v. So his x velocity is going to be v cosine of theta is going to be his x velocity. And his y velocity is going to be v sine of theta. Cool. So this is v cosine of theta. Awesome. Let's just simplify that a little bit to neaten it up. So this is what? 585. This whole term is going to be 0 equals, let's see, her x momentum, if you multiply 45 times 4.80 is around 216, which you'll notice this is similar to what we did above, plus 65v cosine of theta. And keep in mind, I'm going to highlight in yellow. This statement right here is essentially the same thing as this statement, so keep that in mind. And now what we're going to do is I'm going to go ahead and look at the y momentum, okay? And I should circle this x equation because we'll come back to it. So for the y momentum, let's see. So afterwards they're separate and before they're separate. So I'm going to have mass of Rebecca times velocity of Rebecca in the y, plus mass of Dan times velocity of Dan in the y, equals mass of Rebecca times velocity of Rebecca in the y, plus mass of Dan, velocity of Dan in the y. And again, the left-hand side is our momentum initial in the y, and our right-hand side is our momentum final in the y. Okay, so let's plug in some numbers. So mass of Rebecca is what? 45 times her initial y velocity. Oh my goodness, 0. She's not moving in the y. Plus mass of Dan is what? No, his mass is what? 65 times velocity of Dan, 0. Oh my goodness, I love it when things get easy. Mass of Rebecca after is what? 45. Velocity in the y, again, that is going to be what? 8 sine of 53.1 degrees, which I get when I solve to be about 6.3, maybe about 40 for rounding meters per second for Rebecca's velocity initial. So when we put that in, that is going to be what? 6.4 plus mass of Dan is what? 65 times velocity sine theta. Again, let's simplify this a little. Left-hand side simplifies to essentially 0 plus 0 equals, let's see, we have 45 times 6.4, and that is 288 plus 65 v sine of theta. Cool. So that is our y equation. So that is essentially, keep in mind, that is essentially the same thing as this, just a slightly different way to write it. Cool. So now what we essentially have is a good old system of equations. So we can just solve for one thing and another and substitute in. I'll go ahead and go through it real quick, but feel free to stop watching the video if you know how to solve this from here. So I'm just going to erase a little bit, give myself a little space. Okay, so I first rewrote the momentum in the x equation. So what I'm just going to go ahead and do, I'm going to solve for v, and I'm going to plug it into the other equation. So let's go ahead and solve for v. So I'm going to take away 216 from both sides. So let's see, when I do that, so that'll be what? 369 equals 65v cosine of theta. To get v by itself, I'm going to divide by 65 cosine of theta, 65 cosine of theta. So then this will be, this will just be 5.67 divided by cosine of theta. Cool. So now what I can do, so I have this v right here. I can now go ahead and just plug it into my other equation. And again, that equation, if I write it right here, 0 is the left-hand side, what, 288 plus, that was 65v sine theta. And again, I'm plugging in for v what I just got. So 0 equals 288 plus 65 times 5.68 over cosine of theta times sine of theta. Cool. So I have 0 equals 288. Okay, 65 times 5.67 is 369, and then it's sine of theta on top over cosine of theta on the bottom. Again, everything's just multiplied and divided, so I'm just going to write it this way because I can understand a little bit better. So let's see, let's move that 288 to the other side. So it's what? Negative 288 equals 369. Sine of theta over cosine of theta is just going to be tangent of theta. So then I can divide both sides by 369. Cool. And I get negative 0.78 equals tangent of theta. I want to solve for theta, so I'm going to use the inverse tangent. So tangent inverse of negative 0.78, and I get negative 37.9 degrees. Cool. Which that's the same as what we got earlier, 37.9 degrees. And then negative there is just there to say it's below the horizontal. Cool. If we want to solve for the velocity, now all we need to do is just go ahead and plug it back in the theta, back into an equation, solve for velocity. It shouldn't matter which way you do it. So that's just another way to do it. Cool. And again, it'll totally be your call how you want to solve these problems. I like this first method we did with the X and Y momentum tables because I think it's a little more conceptual. However, you're totally welcome to do it more algebraically, like what I did below with like sine theta, cosine theta, all that good stuff. But both ways, same idea, just a different process.